Welcome back, and welcome to the notes for today. We're talking about conservation of energy. What does it mean in science when we say that something is conserved, when a quantity is conserved? Doesn't mean when we talk about changing, conserving energy, don't turn your lights off when you're done. Doesn't mean that. It means that your initial quantity is equal to your final quantity. So however much you start with as far as energy is how much energy you end with. And now it can change form. It can change from one type to another, but the total numbers have got to work out. Okay. So energy can change from potential energy to kinetic energy to heat to elastic potential energy to gravitational potential energy to any form that you can think of, but the total number still has to work out. So here we have a weight that's lifted, and it's starting off with potential energy, gravitational potential energy. After we cut the string and it falls and it accelerates, gravity accelerates, does work on it. That work changes its gravitational potential energy to kinetic energy, and then when that weight does hits this wooden stake, it does work on the stake, and that energy gets converted to heat. So that energy just converts from one form to another, and that's pretty much conservation of energy. Not only does it change form, but the exact amount has got to stay the same. So if we start off with 10,000 joules of gravitational potential energy because we're starting very high up, we do a swan dive into a bucket of water. If we lose gravitational potential energy because we've lost height, okay, the exact amount that we lose in gravitational potential energy has got to show up somewhere else. And in this case, it's showing up as kinetic energy because they're speeding up. So I still have 10,000 joules, the same amount that I started with. When I'm halfway down, I've lost half of my GPE, and it's converted to kinetic energy. I still have 10,000 joules. Okay, when I'm 3/4 of the way to the ground, I still have 10,000 joules. And just before I reach the ground, I've lost all my gravitational potential energy, and I've gained that all in the form of kinetic energy. So I've got 10,000 joules of kinetic energy. So the total amount of energy is conserved. The total amount stays the same. Okay, if we look at a pendulum, okay, so picture that there's a string on this. I couldn't make the animation work with the string, so just bear with me. Where does this, and this is the pendulum, the swinging bob, the swinging ball. Where does the swinging ball have the most potential energy? Specifically the most gravitational potential energy. Okay, what positions? When it's at the ends, when it's at the very right side, and when it's got the very left side, because that's when it's the highest. Okay. When does it have the most kinetic energy? Well, that's at the bottom when it's moving the very fastest. Okay, so if we were to look at a bar graph of kinetic energy versus potential energy, the green being potential energy is maxed out at the very ends. Okay, and blue kinetic energy is maxed out when it's at the bottom. Okay, so the type of energy changes form, but the total amount stays constant. Okay. So if we start off with 10 joules of potential energy at the very left side, how many joules of kinetic energy are we going to have at the bottom? We're going to have 10 joules, because all of that potential energy is going to get converted into kinetic energy. Okay. Now, when I swing a real pendulum, it doesn't swing back and forth up to the exact same height. Each time it swings back a little bit lower, and that's not to say that we're destroying energy. It's just being converted to another form that we can't see, and that form that it's getting converted to is heat. And so each time it swings a little bit lower, a little bit more, that energy is converted to heat, and the room gets a little bit warmer, and that sort of thing. So. Another example, let's say I've got this heavy weight lifted, and right now the energy is starting out in the form of gravitational potential energy. So I like to think of energy as money. So these are Bernabo dollars here, and right now they're at the gravitational potential energy store. Now I can spend these dollars Okay, they can go to different stores, they can go to different forms of energy. Okay, but I still have to have 4 Bernabo dollars no matter what happens. Okay, that money's got to show up somewhere. Okay, if it doesn't, something's wrong. Okay, so it starts off with 4 Bernabo dollars worth of GPE. Okay, when I cut the string, okay, it's going to fall towards the ground, and that energy is going to get converted into kinetic energy. So just before it hits the ground, it's got 4 Bernabo dollars worth of kinetic energy. Okay, and then when it hits the ground with a thud, that energy gets converted into heat, and the ground gets a little bit warmer, the air gets a little bit warmer, the metal gets a little bit warmer, and so all that energy gets converted to heat. Okay, but notice we still have the same amount. Thinking about a bungee jumper, so here we've got a bungee jumper with an elastic cord. Okay, they're going to jump. Okay, and here they're falling, and they're just about to stretch the cord. They haven't stretched it at all, which is why it's still the same thickness. Okay, and then here they've reached the very bottom of their jump. They've stretched the cord at the maximum that it's going to stretch. And we want to talk about the types of energy that we've got in each scenario. Okay, so initially our bungee jumper is starting off with what type of energy? Well, he's got gravitational potential energy because he's above the ground. He doesn't have any elastic potential energy because the elastic cord isn't stretched. Doesn't have any kinetic energy because he's not moving. Okay, so just gravitational potential energy. Okay, so here, okay, he's moving. Okay, and he's still above the ground, and he's just about to stretch the cord, but he hasn't stretched it yet. What kind of energy do we have now? Well, he's still above the ground, so he's got gravitational potential energy. Okay, he's moving, so he's got kinetic energy. Okay, and he hasn't stretched the cord, so he doesn't have elastic potential energy yet. Okay, so here he's stretched the cord. He's reached the bottom of his stretch. He's just about to touch the ground. What type of energy does he have? Well, he's about to touch the ground, so he doesn't have any gravitational potential energy. He stopped moving. Okay, he's about to climb back up. Okay, so he doesn't have any kinetic energy. He's got the cord stretched, which means he's got elastic potential energy, and that pretty much takes care of it. So it just has elastic potential energy. So let's say he starts off with 50 joules of gravitational potential energy, and let's say that at this state he's got only 40 joules of gravitational potential energy. And the question is, how much kinetic energy does he have? And well, he's got to have 50 joules of energy somewhere. So that 10 that he lost in GPE has got to show up as KE. So the answer is just 10. Okay. And at the very bottom, the elastic potential energy would be what? It would be the full 50 joules. Okay. So if we bounce a ball on a floor, okay, we've got another example of energy changing forms in front of us. Energy is changing form constantly all around you. It's just constant, and just so many examples that if you look around, you'll see hundreds all the time. But what kind of energy conversion do we have going on when we bounce a ball? Well, when we drop the ball, okay, the ball is starting with GPE or gravitational potential energy. Okay, just before it hits the ground, it's moving as fast as it's going to move, and it's got 10 joules of kinetic energy. Okay, when the ball hits the ground, it squishes and deforms. That's the only way it can bounce back up, is the fact that it deforms. So when it's squished, it's got 10 joules of elastic potential energy, assuming it doesn't lose any of the heat. Okay, and then when it rebounds, it's going to have 10 joules of kinetic energy. And then if it goes back to the same height, it's going to have 10 joules of GPE again. Okay, so GPE to kinetic energy to elastic potential energy and back to kinetic and back to GPE. Okay, so that's if the ball's perfectly elastic, if it bounces back to the same height. But real balls don't do that. They don't bounce up to the same height. And where does that energy go? We know it can't get destroyed. It's got to show up somewhere. Okay, and that energy is heat. So when I drop a ball, if it starts with 10 joules of GPE, and just before it hits the ground, it's got 10 joules of KE. When it squishes, okay, during that collision with the ground, it's going to lose some of that energy to heat. Okay, so let's say it only stores 8 joules of elastic potential energy. And that means that the remaining 2 joules that doesn't show up anywhere else has got to be in the form of heat. And then it'll bounce back with 8 joules. So now it's got 8 joules of KE and 2 joules of heat. And then here it's got 8 joules of GPE and 2 joules of heat. Okay, and that heat goes to warm the room and that sort of thing. So even though that energy is not available to bounce the ball higher, it's not destroyed. It's just in a different form. How does this happen? Well, if you're an in-person person, remind me to show you this. I've got a cube of these balls that are attached to each other by springs. And when you drop this cube of these things connected by springs, they start jiggling. Okay, that's just like the elastic ball hitting the ground. And when those springs and the balls on the springs start jiggling, that means that they've gained kinetic energy, which means their temperature is increased. And that's really how the energy in the bouncing ball got converted to heat. The atoms on their elastic bonds just got moving and vibrating and faster and that sort of thing. So yeah. Okay. So applying a little bit more math to conservation of energy, we're going to say our initial energy equals our final energy. Now, again, it can change form, and we've got to take into account all the different types of energy. So my initial potential energy plus my initial kinetic energy has to equal my final potential energy plus my final kinetic energy. Okay, so if I start off with 10 joules on this side, I got to have 10 joules on this side, but it can change from one type to the other. Okay, so let's work a problem, or two, I believe. So we've got a 0.25 kilogram ball rolling at 2 meters per second towards a ramp. How high on the other side will it reach? Okay, how much PE will it have at the highest point, and how high above the ground will it reach? Let's just work the how high above the ground will it reach. So let's see. We want to think about this in terms of energy. So initially, do I have any GPE? Okay, I'm on the ground, so I don't have any GPE. Do I have any kinetic energy? Yes, because I'm moving at 2 meters per second. Okay. Do I have any elastic potential energy? No, there's nothing squished or anything like that. I'm not going to throw any elastic problems on these types of problems anyway. So now when it rolls up this ramp, okay, eventually it's going to come to a stop at the top. Okay, before it rolls back down. So how does it have any GPE at this point? Sure it does. It's elevated. Does it have any kinetic energy at this point? Nope. So it starts off with kinetic energy, and it ends up with gravitational potential energy. So let's see what that looks like with the equations a little bit. So PE1 plus KE1 equals PE2 plus KE2. We said I don't have any potential energy initially. It's all in the form of kinetic energy. Okay. And then I don't have any potential energy in the final situation, or I'm sorry, I don't have any kinetic energy in the final situation. I don't know why I didn't scratch that out, but I do have potential energy. Okay, so I wrote the equation 0 equals mv squared over 2 for my initial KE plus mgh for my final GPE plus 0 because this I meant to scratch this out, but I didn't. So for that. And notice what I did here is I crossed out the m's. I didn't cross out the whole equation here. I just crossed out the m's because the m's are going to cancel out. You don't have to do that. You can plug in the m and it'll cancel out when you do your math. But I went ahead and did that. So plugging in for our velocity is 2. Okay, so 2 squared over 2 because we divide by 2 equals gh because we cancel out our m. Okay, so 9.8 times h. We get our height is equal to 0.2 meters. So conservation of energy. And when I give you a problem, on a test or the homework, it's going to look pretty similar to this or the next one. Okay, so I'm not going to be expecting you to think too far out of the box. Here we've got a 25 kilogram rock. And it's going to roll down or slides down a frictionless incline, okay? and we want to know how fast is it moving at the bottom. Okay, so how fast is it moving at the bottom? So this is my initial picture, the rock on the top of the ramp. So do I have any GPE? Sure I do. I'm elevated, so I've got MGH. Do I have any KE? No, I'm at rest. So I'm starting at rest. When I reach the bottom, okay, my final situation, do I have any GPE? No, because I'm at the bottom. My elevation, my height is 0. Do I have any KE? Am I going to be moving? Sure, it's going to be moving. It just slid down the ramp. Okay, so looking at that in our equation form again. So we've got PE1 plus KE1 equals PE2 plus KE2. Okay, my initial potential energy, MGH, plus my initial kinetic energy, which is 0, so 0 for KE, equals my final potential energy, which is 0 because I'm at the bottom of the ramp, okay, plus my kinetic energy, mv squared over 2. So plugging in numbers, 9.8 for G. Well, we crossed out m's again, by the way. 9.8 for G, 5 times that's the height, and we're trying to find V. So multiply by 2, multiply by 5, and take the square root, you get 9.9. So what I'd like you to do is worksheet 6-4. Make sure you show your work and look at these examples if you get stuck, and good luck.